All right, you might be tested on this, and it'll definitely be useful for the future. So we're going to talk about the number of H bonds that the base pairs have. So when we have our DNA, there we show our base pairs often like this. And let's say that we're looking at this particular base pair. From this DNA strand, you might have an adenine, and then it is H bonding with this thymine. And you might think by the way we're representing it that there's only one H bond going between them, but there are actually two. We just don't indicate it. So there are two H bonds going between T and A, and for C and G, this is different. For C and G, there are three H bonds between them. So I have a memory device that I like to use, and it is a visual one. So when you have your letters, T and A, and then you have C and G, I like to extrapolate the points. Let me change the color. So I like to extrapolate the lines that come off of it. So this line would go downward. It would shoot out like that. It would shoot out this way, that way. This line would go that way. This line would go this way, this way, this way, this way, and this way. So if you look over here, the lines cross each other 2 times for the T to A, here and here. So T and A have 2 H bonds between them. C and G will do the same thing. So this one does not go anywhere. Neither does this one, but this one goes through and it penetrates the C. And with the C, it would penetrate the G this way, and it would penetrate the G this way. So we have one penetration, I guess. What a weird word to use. We have one over here, 2, and we have a third one over here. So between the C and the G, there are 3 H bonds. Okay, and this can have a couple of impacts on your DNA. So let's say that we're ignoring the helical structure, that we have a segment of DNA, and both of them have 1, 2, 3 base pairs. 1, 2, 3. Let's assume that all of these base pairs are TA base pairs. So let's represent the H bonds. So this is not just one bond. There are 2 H bonds, another H bond over here, another H bond over here. And then let's say that all of these are C and G base pairs. So we would have 3 hydrogen bonds going for each base pair. You see that comparing these 2 strands of DNA, while they have the same amount of base pairs, this strand has less attraction between it, less H bonds holding them together, and this DNA with the C and Gs have more H bonds going between them. So it would be harder to break these strands apart, this particular DNA, compared to this one, because there is more attraction here. So we can make a summary of this. So more C's and G's, we have more H bonds, which means that there is higher attraction between strands. And as a result of that, they are difficult to break apart. And this also gives them a high melting point. So H bonds are weaker than like polar bonds, and they can be broken with heat. But if you have more of them, they're more stable and they require more heat to break. So because there are more H bonds and more difficult to separate, it has a higher melting point. More energy is needed to break through this one. You can do the same one for the T and A's. So you have more T and A's relative to C and G. You would have less H bonds, less attraction between the strands. Oh, less strand attraction. Easier to separate, which would give them a lower